Welcome back. We are going to start looking at logarithms. We left off in this chapter talking about exponential functions and how we can solve them using like bases, but we can't always do that. And so we need inverse operations. And the inverse operation of an exponential function is a logarithm. And so the logarithm gives us the exponent that the base must be raised in order to get x. If I were to kind of color coordinate what it is that we're talking about, let's say that we have 4 to the third power is equal to 64. That's the exponential form. The log form would start with log. We keep the base, but this time the base is subscripted down below. And then we go to the answer, which is 64, because remember, we would be looking for the exponent, which our exponent in this case is 3. So we have exponential form and then log form. Log is actually an operation. It's just like adding or subtracting or multiplying. It's something that we do to our expression to get an answer. Notice for exponential form that this is all on one level, and then the 3 is superscripted or up top. And for logs, this is all one level, and then your base is subscripted or dropped below. Let's try rewriting these. We're writing from log form to exponential form. Your base always stays your base. So if you've ever played the game left, right, center actually works pretty good for rewriting these. We start on the left, which is our base of 2. We go to the right, which is 3, and that's our exponent, equals center is 8. The left, we have our base is 1/2. We go to the right, our exponent is -4. And then in the center, it's equal to 16. Our base here is 10 on the left. Our exponent is 5 on the right. And our answer is 100,000 in the center. I'm going to start these bottom 3 by writing log, log, and log. Still start on the left. Our base here is 3. Our log base is 3. Right, we have 1/81 equals center -4. Left is a base 5. Right, the answer is 5. Center, our exponent would be 1. This bottom one, I'm going to rewrite over here where we can see it. We have 3/4 to the 0 power is equal to 1. So log, our left is a base of 3/4. Our right is 1 equals our exponent, which is 0. So depending on what it is that we're trying to do, where our x is at, we might write in exponential form from log form, or we might write log form from exponential form. Solving these log equations, we are going to rewrite into exponential form. Our base here is x to the third power is equal to 8/27. So back in section 4.2, we learned that if we have a base that's a variable and we have an exponent that we want to make 1, we use the reciprocal power. The reciprocal of 3 is a third. So I'm going to raise both sides to the 1/3 power. 3 times a third is 1. 8/27 to the 1/3 is 2/3. And so x would be 2/3. Letter B, our base is 4, our exponent is 5/2, and then in our center is x. This I can just straight up put in the calculator, 4 to the 5/2 power. And when I do that, I get 32 for an answer. Letter C, rewriting. Left is 49 for our base. Right is x. Answer is the third root of 7. This one's going to take a little bit of work. We're talking about finding like bases here. Our smaller number between our two bases of 49 and 7 is 7. If I rewrite this right side, that's 7 to the first power, third root. Power over root says that's the 1/3 power. 49 is 7 squared. 2 times x is 2x. Now that these are same bases, we can say 2x is equal to 1/3. Divide by 2 on both sides. 1/3 divided by 2 is 1/6. And so x is 1/6. Logarithmic graphs. They are exactly the opposite of our exponential graphs. We also have different graphs for different bases. So if our base is greater than 1, this time our range is -infinity to infinity because we have nothing stopping us from going down forever or up forever on our graph. This time our range is going to be affected, our domain is affected by our asymptote. And our asymptote, just like on the exponential parent function, starts at 0, but this time it's x is equal to 0. When our base is greater than 1, our graph is still increasing and continuous from 0 to infinity domain. This time the y-axis is our vertical asymptote, which is x is equal to 0. And the graph passes through 1 over a -1, 1, 0, and a 1. So talking about inverses and opposites again, our exponential graph went through 0, 1. Our log graph goes through 1, 0. Our domain and our asymptote still share the same value. And this time, our asymptote and domain are affected by horizontal shifts left and right. And what that would look like then, if I had an equation, let's say log base 3 of x minus 7 plus 2, this minus 7 is a right 7 and moves our asymptote 7 and our domain 7. For our base between 0 and 1, we still have a domain that starts at 0 to infinity. Our range is still negative infinity to infinity. This graph, though, is decreasing from left to right. Continuous, because I don't have to pick up my pencil to draw it on the whole domain. We still have our y-axis as the vertical asymptote, which is x is equal to 0. And we still have 1 over a negative 1, 1, 0, and a 1. And our asymptote there. We will go over those graphs in class. We have to learn how to do the log base in our calculator. So I'm going to skip over examples 3 and 4 and head over to the properties of logarithms. Logarithms. Remember, logs are inverses of exponential functions. And so if I look at the property, if I had x to the third times x to the fourth, the exponent rule here would be to add 3 plus 4 to get 7. So our product property for logs, when we are multiplying, to expand them out, we change that to adding log ax and log ay. The quotient property, if I had x to the 7th over x to the 5th, exponent rules say we would do x to the 7 minus 5. We would subtract. So the quotient property for logs, we rewrite this as subtraction. The power property, when we had, let's say, x to the 5th to the 7th, the rule was to multiply 5 times 7. And so it's kind of similar here. We bring the exponent down and multiply it by the log. So what that would look like is if we had log base 7 of r to the 9th, we'd bring that 9 in front, say 9 times log base 7 of r. The log of 1, no matter what the base is always equal to 0. Again, if I were to rewrite this, that's a to the 0, and anything to the 0 power is 1. So that's why it's always equal to 0. And then if we have a log with the same base as the number, so log base 11 of 11, that's always going to be equal to 1, because remember, when we rewrite that in exponential form, left, right, center, 11 to the first is equal to 11. So we have sum of the logarithms, the difference of the logarithms, multiplied, and then 0 and 1. Let's try a couple. If I'm expanding this out, we have log base 6 of 7. At this multiplication sign is where I write a plus log base 6, because multiplying we expand out by adding, and then of 9. And that's expanded out. We rewrote the multiplication as addition, plus log base 6. Letter B, we have 15 divided by 7. I start with log base 9 of 15. the division changes to subtraction of log base 9/7. So we added this because of the division. Example C, I'm going to rewrite that square root of 8 as 8 to the 1/2 power, power over root, so 1/2 power. That means we're using the power property where that 1/2 drops in front. So it's 1/2 log base 5 of 8. I'm going to do the same thing for example D. I'm going to rewrite that as n to the 2/3 power. The 2/3 drops to the front. 2/3 times log base A of m. Example E. For every multiplication, we write a log base A plus, and then the division is minus. So I start with log base A of m. It's times, so plus log base A. And then we have n. That's times, so plus log base A q. We have division, so that's minus. Now we have more than one thing happening in the denominator, so I'm going to put a parenthesis there. Minus log base A, we have p squared, times, so plus log base A t to the 4th. And our final step to make sure that this is an absolutely expanded form, we have to take our exponents there and drop them to the front. So this first part stays the same. Two times log base A of p, and then minus 4 log base A of t. What happens if we have a whole bunch of logs and we want to condense it back into one? Well, that's okay. We can do that. We're actually just going to take those properties we just learned and go backwards. So cut out all the pluses and minuses and change them back into multiplying and dividing. I'm going to start. I have plus log 3. So log base 3, x plus 2. Plus log 3, if I wanted to cut that out, addition started as multiplying. So times x minus log base 3 started as division. So divided by 2. And that would be condensed form. I've taken that from 3 logs down to just 1. I got to start with moving our stuff in front of the logs back to where they came from, which in this case, they were exponents. So I have log base A of m squared minus log base A of n to the 3rd. Condense this down to a single log. We have m squared minus log base A comes out. That started as division. So over n to the 3rd. Letter D. I have log base 4 of x minus log base 4 started as division, so divided by the y, plus log base 4 started as times z. I put that z in the numerator because there was no set of parentheses around that saying that both of those were supposed to be in the denominator. So that's why it's not down in the denominator and it's up in the numerator. Example E. Start again with moving the stuff in front of the logs back up as exponents. So log base b of r to the fourth minus log base b of s to the fifth. Condense this to a single log base b. We have r to the fourth minus log b started as division, so divided by s to the fifth. We're not going to do that last example, f. But on the bottom, can we rewrite log base 3 of x plus 2 as log base 3x plus log base 3, 2? And the answer to that is no. We have no exponent rule. For adding like bases. Where exponents will change. So this is not a log property either. Meaning when we do like 7x to the fifth plus 8x to the fifth, we only add the 7 and the 8. We don't add the 5s and change it. So if the exponent isn't changing, then we have no property for that. And it can't be a log property either. All right, we made it through that one. Thanks so much for joining me, everybody. I hope you have a great rest of your day.